What if the most advanced technology on Earth isn't sitting in a lab waiting for the future? What if it's already inside the hospital down the street, the plane overhead, and the phone in your pocket, working in near total silence? That's not a hypothetical, but that's the world you're living in right now, and almost nobody has told you about it. We are in the middle of one of the quietest technological revolutions in human history, and it doesn't come with flashing lights or dramatic press conferences. It comes wrapped in the language of physics journals, defense contracts, and hospital equipment manuals, which is exactly why most people have never heard the term at the center of it all: quantum sensing. For decades, when people heard the word quantum, they pictured something distant and theoretical. Quantum computers that might someday break encryption, quantum physics equations scrawled across chalkboards. Something for scientists in white coats, not something for the rest of us. But quantum sensing has slipped past that perception entirely. It has moved from theory to application, from the laboratory to the battlefield, from the research paper to the hospital room, and it has done so without asking for permission or attention. It is already shaping how doctors diagnose disease, how militaries navigate without satellites, how companies search for oil and minerals underground, and how your phone might someday know exactly where you are without ever touching a GPS signal. So let's start with the basic question. What actually is quantum sensing? At its core, it is the practice of using the strange and precise behavior of particles at the quantum level, things like atoms, photons, and electrons, to measure the physical world with a level of accuracy that classical instruments simply cannot reach. A traditional sensor works through bulk physical change. A thermometer expands as it heats up. A compass needle swings because of magnetic force acting on metal. These devices are useful, but they are fundamentally limited by the properties of the materials they're built from, and by the noise and interference of the world around them. Quantum sensors work differently. They exploit properties like superposition, where a particle can exist in multiple states at once, and entanglement, where particles remain connected no matter the distance between them. By using these effects, a quantum sensor can detect a magnetic field so faint it's measured in femtotesla, or a gravitational shift so small it would be completely invisible to any classical device. A single trapped atom can register a change in gravity. A single photon can be enough to detect a shift in a magnetic field. This isn't science fiction. This is measurement pushed to the very edge of what physics allows. Now here's the part that should genuinely surprise you. Some quantum sensing technology isn't new at all. It's been sitting in plain sight for decades, so normalized that we forgot it was ever revolutionary. Think about the MRI machine. If you or someone you know has ever had an MRI scan, you have already interacted with applied quantum technology. Magnetic resonance imaging relies on the quantum behavior of atomic nuclei, specifically the way hydrogen atoms in your body respond to strong magnetic fields and radio waves. Doctors use this every single day to look inside the human body without a single incision, spotting tumors, torn ligaments, and brain abnormalities that would otherwise remain hidden. It is one of the most successful pieces of quantum technology ever built, and it has been saving lives since the 1970s, decades before most people ever heard the word quantum sensing. And it doesn't stop there. Every time you check your phone for directions, order a rideshare, or track a package moving across the country, you're relying on quantum technology too. The global positioning system, the network of satellites that tells your phone exactly where you are on Earth, works because those satellites carry incredibly precise atomic clocks. These clocks use the quantum behavior of atoms, typically cesium or rubidium, to keep time with a level of accuracy that would be impossible using a mechanical or even a standard electronic clock. If those atomic clocks were off by even a fraction of a second, your location on a map could be wrong by miles. So the next time you glance at your phone to see how far you are from home, remember that quantum mechanics is quietly doing the math behind the scenes. These are what scientists sometimes call first-generation quantum technologies, systems built decades ago on well-understood quantum principles, engineered over time into reliable infrastructure that we now take completely for granted. But here's where the story gets interesting, because we are now entering a second wave. A new generation of quantum sensors is moving out of research labs and into real deployment, and this wave is far more advanced, far more sensitive, and in many cases, far more consequential than anything that came before it. Let's talk about one of the most urgent applications driving this new wave: navigation without GPS. It might sound strange to worry about GPS failing, since most of us rely on it constantly and rarely think twice about it. But GPS signals are surprisingly fragile. They travel from satellites thousands of miles away, and by the time they reach a receiver on Earth, they are extremely weak. That makes them vulnerable to jamming and spoofing, where an adversary intentionally blocks or fakes the signal to throw a system off course. For a civilian trying to find a coffee shop, that's an inconvenience. For a military aircraft, a submarine, or an autonomous vehicle operating in a contested environment, that vulnerability could be catastrophic. This is why defense agencies around the world have poured enormous resources into quantum navigation as an alternative. In the United States, DARPA has funded programs specifically designed to build quantum sensors capable of navigating without any satellite signal at all. One striking example involves quantum accelerometers, devices that measure motion with such extraordinary precision that they can track a vehicle's position purely through inertia, essentially calculating exactly how far and in what direction something has moved without ever needing an outside signal. Some of these systems have reportedly achieved positioning accuracy more than 100 times better than the inertial navigation systems used previously. Other approaches use quantum magnetometers, sensors so sensitive to Earth's magnetic field that they can compare tiny variations in that field to detailed magnetic maps and pinpoint a location, similar to how a hiker might use landmarks instead of a compass. One company has built a system that does exactly this for aircraft, feeding magnetic field data into models that determine location without ever touching a satellite. This isn't confined to fighter jets and submarines either. Commercial aviation, shipping, and autonomous trucking are all exploring quantum inertial navigation systems, because the same vulnerability that threatens military operations also threatens the everyday infrastructure that moves goods and people around the planet. Automotive companies have already begun testing quantum accelerometers for use in self-driving vehicles, aiming to integrate this technology into production vehicles within just the next few years. Imagine a future where your car can navigate confidently through a tunnel, a dense city with skyscrapers blocking satellite signals, or a remote area with no cell coverage at all, not because it's guessing, but because it's using quantum precision to track its own motion with pinpoint accuracy. It's worth pausing here to appreciate just how strange this idea really is. A quantum accelerometer doesn't ping a satellite, doesn't send or receive any external signal at all. It works entirely by watching how clouds of ultra-cold atoms respond to motion, using laser pulses to measure their behavior with a precision that borders on unbelievable. Cool a cluster of atoms down to temperatures close to absolute zero, and those atoms become almost perfectly still, almost perfectly predictable, which means any tiny deviation in their motion can be measured with extraordinary accuracy. That deviation is then translated into exact information about how the device carrying it has moved through space. It sounds almost too elegant to be real, atoms so cold and so quiet that their behavior becomes a map of the world around them. But it's already being tested in real vehicles, real aircraft, and real defense platforms today, not decades from now. Now let's move from navigation to something even more personal, your health. This might be the area where quantum sensing has the most potential to touch your life directly, and soon. We already talked about the MRI machine as a first-generation quantum technology, but the next generation of quantum medical sensors is aiming to go much further and much smaller. Consider magnetoencephalography, a mouthful of a term that essentially means measuring the magnetic fields produced by activity in the brain. Every time neurons fire, they generate incredibly faint magnetic signals, so faint that for decades, capturing them required massive, room-sized machines cooled to near absolute zero. But new quantum magnetometers are shrinking that entire process down into wearable, portable devices. Instead of a patient lying motionless inside an enormous machine, researchers are developing helmets and headsets that can map brain activity while a person moves naturally, opens and closes their hand, or even walks around a room. This could transform how doctors study epilepsy, traumatic brain injuries, and neurological disorders, giving them a window into the brain that is both more detailed and dramatically more accessible than anything available today. The heart is getting similar attention. New devices are being developed to capture the magnetic signals generated by your heartbeat, creating a kind of magnetic cardiogram that could offer doctors a more precise, non-invasive way to assess cardiac health. And it goes even deeper than that, down to the level of individual molecules. Researchers have used quantum sensors built from defects in diamond, tiny imperfections at the atomic scale that behave in extraordinarily sensitive ways, to image the atomic structure of single molecules. Traditional imaging techniques like X-ray crystallography require large, well-ordered crystals to work, but this new quantum approach could allow scientists to look directly at individual proteins and biomolecules, revealing structures that were previously invisible. For a field like drug discovery, where understanding the exact shape of a protein can be the difference between a treatment that works and one that fails, this kind of precision could be transformative. There's also serious work being done on wearable diagnostic devices, quantum sensors small enough to sit on your skin, monitoring temperature fluctuations and chemical markers in real time without a single needle or invasive test. Picture a device that could flag the earliest biochemical signs of cancer long before a tumor becomes visible on a traditional scan, or one that could continuously track markers related to aging and regenerative health. Researchers working on this technology have explicitly said their goal is to move quantum tools from the laboratory to the bedside, making this kind of sensing a normal part of everyday healthcare, rather than something confined to specialized research hospitals. There's also growing interest in using quantum sensors to improve existing MRI technology rather than replace it. Some researchers are working on ultra-low field MRI systems that use quantum sensing components, specifically a class of superconducting sensors paired with artificial intelligence to cancel out background noise. The goal is to build MRI machines that are smaller, cheaper, and far less intimidating than the loud, room-sized magnets patients currently have to lie inside for extended periods of time. If that effort succeeds, it could eventually bring imaging capability to smaller clinics and rural hospitals that could never afford or house a traditional MRI machine, closing a gap in access to advanced diagnostics that currently exists between large city hospitals and everywhere else. Beyond the hospital, quantum sensors are also being pointed downward, literally into the Earth itself. Gravimeters, devices that measure incredibly tiny variations in gravitational pull, are being used to map what lies beneath the surface without digging a single hole. Different materials and structures underground, oil deposits, mineral veins, underground water, even hidden tunnels or voids, create subtle changes in the local gravitational field. A sufficiently sensitive gravimeter can detect those changes from above ground, essentially creating an invisible map of what's hidden beneath our feet. This has enormous implications for resource exploration, letting companies locate valuable deposits more efficiently and with less environmental disruption than traditional drilling and testing. It also has implications for infrastructure, helping engineers spot potential sinkholes, monitor the stability of dams, or detect erosion around bridges and tunnels before those problems become dangerous or expensive. There's also meaningful work happening in the world of construction and civil engineering, where gravimeters and related quantum sensors are being tested as tools for pre-construction site surveys, helping engineers detect unstable ground, buried utilities, or unexpected voids before a single foundation is poured. Catching these issues early can save enormous amounts of money and prevent dangerous surprises later in a project, and doing it with a passive, non-invasive sensor, rather than invasive drilling or excavation, is a meaningful shift in how that kind of survey work gets done. Environmental monitoring is another quiet but important frontier. Because quantum sensors can detect such minute changes in magnetic fields, gravity, and other physical properties, they're being explored as tools for tracking early signs of ecological shifts, from subtle changes in ice sheets to fluctuations that might indicate volcanic or seismic activity long before those changes become visible through conventional monitoring. In a world where climate-related risks are becoming more urgent, having sensors capable of catching the earliest possible warning signs could make a meaningful difference in how quickly communities and governments respond. There's one more application worth mentioning before we step back to look at the bigger picture, and that's security. Quantum sensors are also being woven into the infrastructure that protects digital communication. Financial institutions and government agencies are beginning to deploy quantum-based systems that can validate whether a communication network has been tampered with or eavesdropped on, essentially using the ultra-sensitive nature of quantum measurement to detect intrusion in a way that classical monitoring tools cannot. As countries build out national quantum communication networks designed to be resistant to future forms of hacking, quantum sensors play a supporting role, verifying the integrity of those systems and helping ensure that sensitive data, everything from banking transactions to government communications, stays exactly as secure as it's supposed to be. Let's step back for a moment and talk about why all of this is happening now, in this particular window of time. Part of it comes down to money. Governments around the world have recognized that whoever leads in quantum technology will hold a significant strategic advantage, both economically and militarily, and they have started funding this research at a scale that simply didn't exist a decade ago. In the United States, government initiatives have proposed billions of dollars in funding specifically for quantum research over the coming years, channeled through defense research agencies, national laboratories, and standards organizations. The United Kingdom has its own National Quantum Technologies program, funding everything from portable magnetometers for healthcare use and to gravimeters designed for infrastructure monitoring. China has poured resources into its own national quantum sensing programs, with a particular focus on military applications. Even international partnerships have formed around this technology, with countries like the United States, the United Kingdom, and Australia adding quantum sensing to their trilateral defense technology cooperation framework. It also helps to understand just how differently various countries are approaching this race. In the United States, the emphasis tends to fall on defense applications and public-private partnerships, with agencies funding early-stage research and then encouraging private companies to take that research and turn it into deployable products. That approach has already produced a wave of well-funded startups, some backed by hundreds of millions of dollars in venture capital, working specifically on quantum navigation, quantum medical sensing, and quantum-enhanced security. In Europe, the approach has leaned more heavily on coordinated, publicly funded programs, with national quantum strategies in countries like the United Kingdom and Germany funding both academic research and early-stage commercialization efforts, often with a stronger emphasis on healthcare and infrastructure than on defense alone. In Asia, particularly in China and Japan, government coordination tends to be even more centralized, with national laboratories driving much of the fundamental research before handing successful technologies off to industry. No single approach has proven definitively superior, but the competition between these different strategies is itself accelerating the pace of development, because no major economy wants to be left behind in a technology this consequential. This isn't just government money either. Private investment has surged as well, with companies raising hundreds of millions of dollars to develop quantum sensing products for defense, healthcare, and industrial use. Analysts tracking this space describe a market that is growing rapidly, expanding at double-digit rates year over year, driven by defense modernization, healthcare adoption, and the increasing need for navigation systems that don't depend on vulnerable satellite signals. Whether the total market is worth a few $100 million today or closer to $1 billion, depending on which analysis you read, the trajectory tells the same story. This is not a speculative technology anymore. It is transitioning from laboratory prototypes into products that generate real revenue, and that transition is accelerating. There's also a technical reason this is happening now, and it has to do with miniaturization. For a long time, quantum sensors required enormous, delicate laboratory setups, vacuum chambers, cryogenic cooling systems, and rooms full of specialized equipment just to keep a single sensor stable. That made them powerful, but completely impractical outside of a research environment. Over the last several years, engineers have made major strides in shrinking that infrastructure down. New manufacturing techniques, including advanced forms of chip fabrication and even certain types of three-dimensional printing, are being used to build smaller, more rugged versions of the vacuum chambers and magnetic shielding that quantum sensors need, cutting both the cost and the development time dramatically. Some researchers have even found ways to create portable atomic clocks that don't require the deep cryogenic cooling that used to be essential, opening the door to devices that could eventually be small enough and cheap enough to embed in everyday consumer electronics. Which brings us to a genuinely fascinating possibility: quantum sensors inside your smartphone. Researchers have already demonstrated that OLED displays, the exact same kind of screen technology found in many modern smartphones and televisions, can be used to detect and map magnetic fields with a technique borrowed directly from quantum sensing principles. This research is still in its early stages, and it's important to be honest about that. This is not a feature you'll find in a phone on store shelves next year. But it points toward a future where the device already sitting in your pocket could gain entirely new sensing capabilities without requiring bulky new hardware, simply by rethinking how the components already inside your phone can be used. Of course, none of this comes without real challenges, and it would be misleading to present quantum sensing as a technology with no obstacles left to overcome. These sensors are still, in many cases, expensive to build and maintain. The most sensitive quantum devices are also often the most fragile, sensitive not just to the signals scientists want to measure, but to vibration, temperature fluctuations, and electromagnetic noise from the surrounding environment. Taking a sensor that works beautifully in a controlled laboratory and making it rugged enough to survive inside a moving vehicle, a submarine, or a piece of battlefield equipment is a genuinely difficult engineering problem, and it's one that companies and researchers are actively working to solve. There's also a workforce challenge. Quantum physics and quantum engineering require highly specialized training, and there simply aren't enough experts in the world yet to meet the growing demand from companies racing to commercialize this technology. Universities and governments are responding by expanding quantum education programs, but building that talent pipeline takes years, not months. It's also worth noting how this technology tends to move once it does mature, because the pattern has repeated itself again and again throughout the history of physics-driven innovation. A capability starts out enormous, expensive, and confined to a handful of specialized institutions capable of affording it. Over time, engineers find ways to shrink it, cheapen it, and ruggedize it, until eventually it becomes small and affordable enough to embed into ordinary consumer products without anyone thinking twice. The first computers filled entire rooms and were operated exclusively by governments and universities. The first GPS receivers were bulky, expensive, and limited to military and scientific use. Today, both of those capabilities sit comfortably inside a device that fits in your palm and costs a few $100s. There's no guarantee that quantum sensing will follow exactly the same path, and the physics involved is genuinely more delicate than anything a smartphone chip has had to contend with before. But the underlying pattern of miniaturization and cost reduction that has defined nearly every transformative technology in modern history is already visibly underway here too, in atomic clocks that no longer need deep cryogenic cooling, and in sensor components small enough to fit on a chip rather than fill a laboratory bench. There are also broader questions worth sitting with, questions that go beyond the technology itself. As quantum sensors become sensitive enough to detect the magnetic signature of a submarine from a distance, or to map underground structures with startling precision, they raise real questions about privacy, surveillance, and security. A technology capable of sensing the world with this level of detail is not neutral. It can be used to save lives in a hospital, and it can also be used to track movement, monitor infrastructure, or gather intelligence in ways that weren't previously possible. As this technology matures and spreads, societies will need to grapple with how it's regulated, who has access to it, and what boundaries should exist around its use, the same way we've had to grapple with the implications of GPS, surveillance cameras, and other powerful sensing technologies before it. Still, when you step back and look at the full picture, what's most striking about quantum sensing isn't any single breakthrough. It's the sheer breadth of what's happening simultaneously across completely different fields, all converging around the same underlying physics. In hospitals, researchers are working toward wearable sensors that could catch disease earlier than ever before. In defense and transportation, engineers are building navigation systems that no longer depend on vulnerable satellites. In resource exploration, companies are mapping what lies beneath the Earth's surface without ever breaking ground. In consumer electronics, researchers are laying the groundwork for sensing capabilities that could one day live inside the device in your pocket. Each of these threads is being pulled forward by its own set of researchers, companies, and government programs. And yet, they all trace back to the same fundamental idea that by working at the level of individual atoms and photons, we can measure the world with a precision that was simply impossible just a generation ago. This is why the framing at the beginning of this video matters so much. Quantum sensing isn't a technology waiting quietly in some distant future, arriving only after quantum computers become mainstream or make headline news. It's already here, and in some forms, it has been here for decades without most of us ever realizing it. Every MRI scan, every GPS signal bouncing between satellites and your phone is proof that this technology has already earned its place in our daily lives. What's changing now is the scale and the sensitivity, as a second wave of smaller, sharper, more capable quantum sensors moves from research labs into hospitals, vehicles, and eventually, perhaps, into the palm of your hand. So the next time you glance down at a map on your phone, or watch a doctor review an MRI scan, or hear about a self-driving vehicle navigating flawlessly through a tunnel with no satellite signal in sight, remember what's actually happening underneath the surface. Somewhere in that process, a quantum sensor, built on principles so precise they can measure the world atom by atom, is quietly doing its job. Not with fanfare, not with headlines, just with a level of accuracy that classical technology could never have delivered, working silently in the background of a world that has already, without asking permission, become quantum. And the quieter it stays, the more it proves the point the future doesn't always arrive with an announcement. Sometimes it just arrives and waits patiently for the rest of us to notice.